Hello everyone and welcome to this video tutorial on how to fit a second order underdamped model to a step response system. Today I will be explaining how to approximate a second order transfer function of a system just by looking at its response with a graphic. In order to do this, I will use as an example an electric vehicle model. First up, what I did was to draw this free body diagram for a car when it is moving. If we apply Newton's second law, then we obtain this equation that describes the motion of a car. And what does each one of those forces mean? Well, Fpe is the force of the motor that is moving the car. Fhc is the weight of the car acting against the traction force when it is facing on a slope. FRR is the rolling resistance, that is an interaction between the wheels and the road and is opposing the motion. And FAP, that is the track resistance of the car when it starts to move. As you can see, we have these formulas for calculating the forces, but FP doesn't have any formula. That's because we will obtain it by estimating the torque of the motor and dividing it by the radius of the wheels of the car. And well, how do we obtain the torque of the motor? We have to model it as well, and in this case I chose to model it as a shunt DC motor, which has this equivalent circuit, and is described by these differential equations. Now, what I did in order to get the response of the system was to implement these differential equations on a block diagram alongside the equation that describes the motion of the car, and through Simulink I was able to obtain the response of the system that was implemented through block diagram. So I will show that in a minute, but first a quick review of the second order shutdown model. So what we have here is the general form of a second order system transfer function. And well, what we are going to do is just to estimate the overshoot value, that is the difference between the peak value and the settling value with respect to the settling value, and from that we will obtain zeta, or the damping ratio, that is this value over here. Then we are going to measure the settling time at from the graphic, and once we have calculated the damping ratio, we are going to be able to estimate omega n when we measure as well the settling time. And then once we have the omega n, or natural frequency, we will be able to calculate k. And well, k is obtained by omega n squared times settling value, that is this value over here, divided by UF, where UF is a step input value that I will show in a minute. So let's get over with this and head to the Simulink model. And this is the Simulink model I was talking about. This is the model of the car. This is the model of the motor with an input of 400. Let's remember that value later on when we have to divide the settling value by the input value. So what we are doing here is just inputting a value for the voltage of the armature of the motor and obtaining the velocity of the car as a response. Here I have already placed the cursors, so what we have to do is to place the cursor 1 in the peak value, as precise as you can, just zoom in to make a more accurate measure, and the other cursor is placed on the value on which the function has settled. So we have to calculate the difference between the peak and the settling value and divide it by the settling value in order to have the overshoot, just like I will show you now. Here we see this was the peak value, 231.1 measured with the cursor, minus 186.8, that is the settling value, also measured with the cursor, divided by 186.8. There we have the overshoot, that is 0.23715, and if we solve this equation for zeta, we obtain this, and when substituting the overshoot calculated, we obtain this value for the damping ratio. Now, how to calculate the omega n? Well, we'll see that. Well, here I will be measuring the settling time. And how do I do that? Well, we know that the system has to stay within a 2% limit of the settling value. That is, I multiply 1.02 times 186.8, that I know is my settling value, and I obtain 190.536. So I place the cursor in that value in here. Make sure that when you measure the settling time, you are using the screen cursors and the horizontal and vertical are activated. So I just input that number in here, and then I multiplied 186 times 0.98 and obtain this value. That is the lower limit, that is at 2% lower than the settling value. And then I just zoomed in and look at the last time that the system crossed that point. And well, you have to zoom in a lot to have a more accurate measurement, but I already done that and I obtained this time of 57.889. I substituted that into this equation, that is this equation solved for omega n, and obtained the value of natural frequency. So now we just have to obtain the gain. And the gain, we don't have to measure anything in the response, and we just have to use this formula. Omega n we have calculated previously. YF we know it's 186.8 as we have measured a lot before, and 400 is the input step value that I have mentioned just when I showed the Simulink model. So if we put those numbers in the formula, we obtain this value. And now we have all the values we need. We have the damping ratio, we have omega n, and we have k, and we just have to substitute them in here, 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 and here. And we have this transfer function that should look similar to the response we were basing on to make the measurements. And that is all, and thank you very much for watching. See you later.